Lesson 8.1, Distribution of the Sample Mean. We will be able to describe the distribution of the sample mean for non-normal and normal populations by the end of this lesson. Before we begin, let's look at what we covered in Chapter 7. Chapter 7, we covered uniform distributions and normal distributions. With a normal distribution, we're able to find any percentage or random variable from a given percentage. So today in 8.1 we are going to be covering this section here. So sample mean x bar for one population. So random variable is a numerical measure of the outcome of a probability experiment. Statistics such as the sample mean x bar are also random variables. Statistics are random variables because the value of a statistic varies from sample to sample. For this reason, statistics have probability distributions associated with them. For example, there's a probability distribution for the sample means and sample proportion. So basically what this is saying is that we have some kind of a distribution. So before we've worked with a distribution, say x for our heights. And we can create a histogram and getting approximately a normal shape curve. Now, what that paragraph just said is the sample mean also has a distribution. So when we talk about distribution, we say that it has a shape, it has a mean, and it has a spread. So we can say that for heights, individual heights in here, we could take a group of heights, find the mean, and then plot it. And then we could do that. So these are a whole bunch of different means and then plotted. Here is you just have heights, different heights that are plotted. Okay. Let's look at an example. In 2015, the mean annual U.S. household income was approximately $79,263. The households in the current population survey was determined by chance, random sampling. A second random sample of households would likely lead to a different sample mean, such as $78,518. And a third sample of households would likely lead to a third sample mean, such as $79,081. Because the household selected will vary from sample to sample, the sample mean of household income will also vary from sample to sample. For this reason, the sample mean is a random variable, so it has a probability distribution. So that example basically talked about like this, these curves. So now we're talking about the sample means that we have for average U.S. household incomes. So instead of average heights, we're talking about average household incomes. The sample mean will vary from sample to sample. Our goal in this section is to describe the distribution of the sample mean. Remember, when we describe a distribution, we do so in terms of its shape, center, and spread. So what is a sampling distribution of a statistic? It is a probability distribution for all possible values of the statistic computed from a sample of size n. And then what is the sampling distribution of the sample mean x bar? So the first part was kind of what we've done before, so thinking about just our heights. Now we're talking about average heights and then plotting them. This is all possible values of the random variable x bar computed from a sample of size n from a population with mean mu and standard deviation sigma. We have 3 steps for determining the sampling distribution of the sample mean. What you first do is obtain a simple random sample of size n, then compute the sample mean, and then assuming that we are sampling from a finite population, repeat steps 1 and 2 until all distinct simple random samples of size n have been obtained. So you obtain a simple random sample, find the mean, and then now that's your point. Unlike here before, you're just obtaining a simple random sample and then plotting it. So you just have these 2 extra steps for sample mean. So let's talk about the shape. What is the shape of the distribution of the sample mean as the sample size increases? It becomes approximately normal as the sample size n increases, regardless of the shape of the underlying population. So exactly how big does it have to be for it to be normally distributed? Shape n has to be greater than or equal to 30 for the sample mean x bar to be approximately normal if the parent population is not known to be normal. So if we have a sample size of 30 and above, we can assume it is normally distributed because of the central limit theorem. All right, let's label this A, B, and C. I would like you to rank each distribution from lowest to highest in terms of the sample size required for the distribution of the sample mean to be approximately normally distributed. So which one's already normally distributed? B, so that's going to take the least amount of a sample size. And then it's going to be A, and then skewed left or skewed right is going to take the most in terms of sample size for it to become normally distributed. The center is known as mu sub x bar. So as the sample size n increases, what does the mean of the distribution of the sample mean x bar equal? It is equal to the mean of the underlying population. So basically the center is not affected. So when you're talking about individual heights compared to mean heights, the center is not affected. The mean for either will still be the same, or they'll be equal, in other words. What about the spread? So as the sample size n increases, what happens to the standard deviation of the distribution of the sample mean? So when you think of standard deviation, as n increases, are you going to become more accurate of what the population is or less accurate? The higher the sample size, the more accurate you're going to be. The more accurate you're going to be, the smaller standard of error or margin of error, which is also your standard deviation. So as your n increases, your standard deviation should decrease because you'll be getting more accurate results. And the standard deviation is represented by sigma sub x bar. Okay, and you can also think of this as standard error of the mean of the sampling distribution x bar. All right, let's list the formulas for the mean. So I told you the mean did not change. So mu of x bar is just equal to mu. And the standard deviation is going to decrease. So if you have the standard deviation of the regular, it's going to decrease when you take the square root of the population size. Okay, and then independence. You'll need to do this every time. N is going to have to always be less than or equal to 0.05 of n. This is your sample size, that's your population size. I would like you to try the example from the above definitions I provided. The IQ scores of individuals are modeled by a normal random variable with mean mu equaling 100 and standard deviation sigma equaling 15. The distribution of the sample mean x bar, the mean IQ of a simple random sample of n equals 9 individuals is normal, with mu x bar equaling, that should be just equal to mu, so 100, and the standard deviation sigma sub x bar, which is sigma 15 over the square root of n, which is 9. Square root of 9 is 3, so 15 divided by 3 is 5. Let's look at another example. The IQx of humans is approximately normally distributed with mean mu equaling 100 and standard deviation sigma equaling 15. Compute the probability that a simple random sample of n equaling 10 results in a sample mean greater than 110. That is, compute probability that x bar is greater than 110. So in your homework, they're not going to give you this part. You're going to have to figure out from this wording. So the key word here is sample mean. Okay, you're finding probability, so you should write P. Sample mean, you should think x bar. This is sample mean, is greater than 110. So on your own, you should be able to write this. Okay, so whenever we see this, we should know that we're going to be using, hopefully, the normal curve, because that's what we've only been taught. So is it normally distributed? It is, because it states it is. We cannot use a central limit theorem in neither of these examples because it's less than 30. So in order for it to be used, we need to know it is normally distributed, and it is. So now that we know it's normally distributed, we can apply what we learned in chapter 7, the normal distribution, to figure out this answer. Okay, the only thing that changes is that you have now, you're going to need to use mu sub x bar, since we're working with x bar, and sigma sub x bar. So what is mu sub x bar? That is 100, and sigma sub x bar is 15 over the square root of 10. So this will be number 6 on your calculator, your normal distribution. The only really thing that's changing is your standard deviation. Okay, so if we go number 6, we need to do lower first, then upper. So lower is 110, upper 9s, mean and standard deviation. The mean was 100, standard deviation was square root of 15. Oops, sorry, not square root of 15. 15 divided by square root of 10. in that parenthesis, then end it one more time for the normal parenthesis. 0.0175.